The atomic nucleus is discovered in 1911 by Ernest Rutherford, and according to this, nucleus is a small, dense region consisting of protons and neutrons at the center of an atom. The atomic nucleus is a bound quantum system of atom itself, and so exists in different quantum states. These quantum states are characterized by energies and angular momentum. In this video lecture, we'll be going to tackle about the different nuclear properties. So the first nuclear property that we're going to talk about is the atomic number. So the atomic number is the number of protons in the nucleus of an atom. So the number of protons in the nucleus in fact defines for us the identity of the nucleus. So for example, in carbon is defined as the element which has 6 protons in the nucleus. So the 6 protons is also the atomic number of carbon. On the other hand, we also have the number of neutrons in the nucleus. And the number of neutrons is not going to change the identity of the element. Instead, we call them isotopes. So in carbon, for example, there might be 6 neutrons in the nucleus, but there might be other numbers of neutrons in that nucleus. In those cases, we would say that this is the isotopes of carbons. We can always find the total number of nucleons by simply adding the number of protons and neutrons. So for example, if we have 6 protons and then 6 neutrons in carbon, we would refer to this element as carbon-12, which means that there are 12 total number of nucleons in that nucleus. Another nuclear property that we're going to talk is the mass number. So the mass number is the total number of the nucleons in an atom. This includes both protons and the neutrons. So the atomic number defines an atom itself, and this is the number of the protons. So we refer to as Z. The neutron number is the number of the neutron, and we refer to as N. The total number of nucleons, or the mass number, is simply be the sum of all the protons and all the neutrons. That's a Z plus N. Another nuclear property is the natural abundance. So each stable isotopes has a particular natural abundance. Stable isotopes are isotopes that stick around and be able to measure the measure of how many types of isotopes is called the natural abundance. Another nuclear property that we're going to talk is the nuclear density. So the nuclear density is the density of the atomic nucleus. So we can calculate the density by having this formula. Density is equals to the mass of the nucleus divided by the volume of the nucleus. So the last nuclear property that we're going to tackle is the atomic weight. So the atomic weight is the number of grams in 1 mole of an element at a natural abundance. In periodic table, we listed below the element, and this number tells us how many grams of element would be in 1 mole of that element.
Good day, everyone. I am Teacher Nelsie.
And I am Teacher Jessa.
And we are going to discuss which proton and neutron numbers result in stable nuclei. There is factors that affects nuclear stability, and that is that nuclei with even numbers of protons and neutrons are more likely to be stable than those with odd numbers of protons and neutrons. And just to give an idea, if you look at this table here, this list of all the known stable nuclides, and we can see that the vast majority have even numbers of protons and neutrons. And when even one of those, either the neutrons or the protons, is odd, the number of stable nuclei dropped significantly. And there are only 5 stable nuclei that have both odd protons and neutrons. In addition to just looking at whether the number of protons are even or odd, it turns out that there are specific number of protons and neutrons that are particularly stable, even more stable than just being even, and those are called magic numbers. And so the magic numbers of neutrons and protons are 2, 8, 20, 28, 50, 82, and 126. So if you have even numbers of neutrons and protons, then that nuclide is more likely to be stable. If we have a magic number of either the protons or neutrons that are even more likely to be stable, that doesn't guarantee, just because it has even numbers of protons and neutrons, or just you guys as a magic number, that doesn't guarantee that it's gonna be stable. It's just more likely to be stable.
This is a problem that I asked related to this concept. And what I'll do is I will give you a pair of nuclides and I will tell you that one of them is stable and the other one is radioactive. I want you to predict which one is stable and which one is ready to active without using the NZ ratios. So what we're going to do is we're going to figure out the number of neutrons and protons. And then use this even add magic number concept to decide which one is more likely to be stable and which one is more likely to radioactive. So, in this example, they're both sodium. So I am going toward the periodic table and I am going to look up with the atomic number of sodium. So sodium is atomic number 11. So for both of this nuclide, Z is 11. And then you get the number of neutrons. I just do the mass number minus the number of proton. For sodium 23, it has 12 neutrons. For sodium 24, it has 13. So we can see I've got an even number or odd number of protons in both cases. But because I have an even number of neutrons for sodium 23, it's more likely to be stable in a sodium 24 because both of its protons and neutrons this one is more likely to be radioactive and sodium 23 is the more likely to be stable.
A pleasant day, everyone. I'm teacher Mary Marta. And I'm teacher Charlene. And we are the lecturer for this topic, Calculate Nuclear Binding Energy.
The nuclear binding energy is defined as the amount of energy required to break apart a nucleus into its component nucleons. The conversion of mass defect into energy can be calculated using Einstein equation. E is equal to mc squared, where E is the amount of energy and m is the mass and c is the speed of light, which is equal to 2.99792 times 10 raised to 8 meter per second. So, we can replace the E for Einstein by E sub b being the nuclear binding energy. And we have the mass here by the mass defect, and we have the c squared. So that nuclear binding energy can be an expression of E sub b is equal to the mass defect times the square of the speed of light, where E sub b is the nuclear binding energy, the delta M is the mass defect, and the mass defect can be computed by taking the difference between the mass calculated minus the mass experimental, where we can say that the mass calculated is the theoretical mass of the nuclei and this is referring to the mass of the proton. The total mass of the proton is the nuclei by multiplying it by the total number of protons in the nuclei, which is prepared as the atomic number as well, and the total number of neutron times the mass of the neutron. Again, on the earlier discussion, you can compute the number of neutrons by deducting the number of proton from the mass number, okay? And we're given here the value for the mass of the proton, which is equal also the mass of an hydrogen atom, which has a 1 proton and 0 neutron. We have the mass in 1.008 atomic mass unit, and the neutron has a mass of 1.008665 atomic mass unit. And 1 atomic mass unit is a very useful conversion. Later, 1 atomic mass unit is equal to 1.66 0.054 times 10 raised to negative 27 kilogram. And from a Bugatti's number, from your general chemistry, a mole of a substance is equal to 6.022 times 10 raised to 23 atoms on particles per mole.
Let us say an example on how to compute the binding energy of a nuclei. For our example, we are asked to calculate the nuclear binding energy of lithium-7 nucleus. If the experimentally observed mass of lithium-7 atom is 7.01600 atomic mass unit, and you're asked how much the nuclear binding energy of a mole of lithium. For the solution, since lithium-7 has atomic number of 3 and that represents the number of protons, which is the charge, the positive charge, and the mass number 7. So 7 minus 3 would give you the number of neutron. Okay, so if you take the equation a while ago, for the computation of the mass calculated or the theoretical mass of a nuclei, that is the number of proton times the mass of proton plus the number of neutron times the mass of neutron. Since we have 3 protons and 4 neutrons, we can substitute it here. Okay, we have 3 protons multiplied by the mass of proton, which is 1.007825 atomic mass unit as given here. And we have 4 neutrons multiplied by the mass of neutron, 1.008665 atomic mass unit, and that will give you the mass calculated 7.058135 atomic mass unit. Okay, to compute the mass defect, that is the difference between mass calculated minus the mass experimental of the nucleus, and this time we are given the mass of the lithium-7 atom. Okay, so we plug in the value. We have the calculated here and the given mass of lithium-7, 7.01600 atomic mass unit, and that gives you a mass effect of 0.042135 atomic mass unit. This can be converted atomic mass unit per nucleus of lithium-7. Okay, we convert the atomic mass unit to kilogram. By this factor, that one atomic mass unit is 1.6604 times 10 raised to negative 27 kilogram for atomic mass unit. So the atomic mass unit here, the AMU, will cancel out. That will give you the mass effect 6.9967 times 10 raised to negative 29 kilogram per nucleus of lithium-7. Okay, moving on for the equation, using the Einstein equation for energy, combined conversion of mass into energy. Okay, we have the mass defect into binding energy. We have substitute that value that we obtained a while ago, and we have the constant for the speed of light. We square that, and that will give you a value of the binding energy 6.2883 times 10 raised to negative 12 kilogram m squared per second squared per nucleus of lithium. Since 1 joule is kilogram meter squared per second, therefore this unit is joule per nucleus of lithium-7. Okay, to compute for the binding energy per mole of lithium-7, we use the Avogadro's number since for every 1 atom of lithium-7 there is 1 nucleus, and in 1 mole according to Bugatti's, there is 6.022 times 10 raised to 23 atoms. The unit atoms cancel out here, the nucleus cancel out, and that leaves you the unit joule per mole of lithium-7.